It's entirely possible that the last couple of examples gave the mistaken impression that optimization problems has to do exclusively with the cardboard box manufacturing industry. But on the contrary, as example 2 is going to show us, it also has to do with making fences. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders on a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so step 1, let's draw ourselves a picture. Take out your crayons and let's get creative. All right, we need a river. It is roughly straight, and well, I'm going to say that there's like some sort of current in it, so I need some current lines there, right? Oh, yes, I can really see. I don't know. I think maybe one too many current lines there. Okay, no, maybe put one there. That looks good. All right, need some fish. Let's see, what color is a fish? Fish is purple, right? So ask the vegetarian what color fish are. Okay, whatever. All right. And, oh, maybe I should have made those things gold. That would have made sense. And goldfish. There we go. They're goldfish. Gold and purple fish. Okay, now let's get this fence color going on here. And we only want 3 sides of a rectangle because the 4th side of that rectangle is going to be the river. So imagine, if you will, that there are some cows up in here and they get to sip at the river, maybe even get themselves a little fish. Probably not because they're herbivores. All right. Okay, so what else do we have? We have a fence there along the river, and we have a total of 2,400 feet of fence. That's a perimeter, isn't it? So our perimeter, it's kind of a semi-perimeter because it doesn't include the river part of it. So I'll just call this fencing. Fencing is equal to 2,400 feet, and that's probably going to come up in some kind of capacity. And what are we doing? We are trying to find the largest area. We're maximizing the area of this rectangular paddock. Max area. It is a rectangle. How do you find the area of a rectangle? Well, okay, so this is going to lead us to boop boop, our primary equation. We need an area equation of a rectangle, which of course is a length times a width, or base times height, whatever you want to call it. And we can choose some variables here. How about we say that's the length and that's the width there. All right. And then as we have seen before in the previous exercises, we've got one too many independent variable. We have to get rid of one of them. And we can do that with this fencing equation. It's not really an equation yet, but we're going to turn it into one. And this is going to form our secondary equation. So second area is going to be our fencing, which is 2,400 feet, should be equal to, we have 2 of these W's. Let me label it so it's obvious. 2 W's and an L. Okay. And now we're going to use this as a system of equations. We're going to solve by substitution. We're going to take one of these variables, solve for one of them, so we can stick it in here. Take a look. Which one of these is easier to solve for? Is it W? Is it L? Let's solve for L. L is equal to 2,400 minus 2W. And we will take that and kindly insert it into L into this equation here in order to get a primary equation with just a single independent variable. All right, okay, so here we got our area equation is equal to parentheses 2,400 minus 2W times another W. Wow, that's fairly simple. It's another polynomial equation, and it looks like it's going to be quadratic. Let's expand it. 2,400W minus 2W squared. There we go. So there's our primary equation whittled down to a single independent variable. What's next? We found primary, we found secondary, we drew a picture. What is next is the feasible domain. As a polynomial equation, of course, the domain is all real numbers. But that doesn't make sense in this particular case. We are using W as our independent variable, is what the whole thing is going to depend upon. So let's think about the smallest and the biggest value of W. Smallest. Well, our width, the smallest it could possibly be is 0, but not actually 0. Go away. Not you guys. You guys stick around. W is equal to 0, but not actually 0. It's going to be greater than 0, right? And then the largest. The largest is going to come from using the entire bit of fence for the entire bit of fence for the W's. So all 24 is going to be for 2 of those W's. If I had used L instead, then all 2400 be used for L. But here we've got 2 W's. So we've got 2W, writing with a laser, 2W is equal to 2400. So W is equal to 1200. Not actually equal to, it's got to be smaller than that. So we're going to set our domain as 0 is less than W, which is less than 1200. Once again, we have ourselves an open interval. Hey, but it's quadratic. Since it is quadratic, it's only going to have a single turning point. And guess what? Look, the leading coefficient of the W, it's negative, which means it's a parabola like this. So we're pretty much guaranteed a maximum. You can't use like pre-calculus arguments like that, though, on a calculus test. We're still going to have to base it all in calculus, and we'll do that in the next video.